In this video, we're going to look at properties of logarithms. So we're not going to get into logarithmic functions the same level we did with our exponential functions, but you could always look back in a textbook and review that. But we are going to focus on some properties of logarithms, which are going to be necessary as you move on into your calculus sequence. Some quick reminder or a quick review, logarithms are the inverse of exponentials. So logarithms allow us to solve for an exponent in an exponential form. I think that this is an important idea because the concept of a logarithm is sometimes hard for us to wrap our head around. What is it actually solving for? That idea is tricky. So really what we're doing is we're just isolating an exponent. So converting between exponential and logarithmic forms, if I've got log base b of x is equal to y, that's equivalent to b to the y equals x. So notice if I consider my exponential form b to the y equals x, that exponent is y, and in my logarithmic form, that's what's isolated. Y is by itself. For logarithms, the base b has to be greater than 0 and b cannot equal 1. This is the same rules that we have for our base of our exponent as our exponential expression as well. Convert from logarithmic to exponential form. This conversion, I think, is a little bit more straightforward. We're going to start with our base. We're going to raise it to whatever it's equal to, and then set it equal to the argument of the logarithm. So this becomes 3 squared equals 9. That's the exponential form of this logarithm. Converting from exponential form to logarithmic form is a little bit trickier. I always start with the knowledge that a logarithm isolates the exponent. So it's going to be 2 equals. The base of my exponential is the base of my logarithm. So this is a log of base 5. And then the argument is what the exponential was originally equal to, or whatever's left, right? Process of elimination there. So 5 squared equals 25 is equivalent to 2 equals log base 5 of 25. Evaluating logarithms. A lot of technology will do this for you, but we really want to understand what this logarithm is solving for. So if I'm trying to evaluate log base 4 of 64, what I'm going to think is 4 to what power is equal to 64? Well, 4 cubed is 64, so log base 4 of 64 is 3. Log base 2 of 1 over 32. To figure out what this equals, we're going to think 2 to what power equals 1 over 32. When I'm raising a whole number to a power and I end up with a fraction, that tells me that my integer or my exponent was negative. So I'm thinking then 2 to what power is 32, and that would be 5. So this is 2 to the negative 5th power equals 1 over 32. Log base 2 of 1 over 32 equals negative 5. A quick review of our properties of logarithms. We have the product rule that says log base a of m times n is equal to log base a of m plus log base a of n. The power rule says log base a of m to some power is equal to n times log base a of m. The quotient rule, log base a of m divided by n is equal to log base a of m minus log base a of n. Be careful with the quotient rule because with subtraction, our order does matter. So it's always that numerator that comes first minus the denominator. The change of base rule, log base a of m. So the change of base just says we can take any logarithm of any base and rewrite it as any other base. So log base a of m is equal to log base b of m divided by log base b of a. Now, the most common conversions for change of base is going to be our common log or a base 10 logarithm and a natural log base e, which is we're going to see in the next example. Some other properties, log base a of a is 1. This is an inverse property. Or excuse me, that's not an inverse property. essentially a to the first power is equal to a. So log base a of a is 1. Log base a of 1 is 0 because a to the 0 power is 1. So anything raised to a power of 0 is 1. Log base a of a to the x, here's our inverse properties. Because log base a is the inverse of a to the x power, those undo each other. That equals x. Likewise, a to the log base a of x. So a to some power is the inverse of log base a. So those undo each other. This equals x. Rewrite log base 4 of 8 as a common log with base 10 and a natural log base e. So log base 4 of 8 is the same as log of 8 divided by log of 4. That common log, we don't actually write the base. So log of 8 is implied as log base 10 of 8, similar to a square root where we don't write the 2 for our index. This is also equal to the natural log of 8 divided by the natural log of 4. So we can change our base to whatever we want it to be, but most typically we're going to use our common log or our natural log when we're using the change of base rules. The next set of examples, we're going to express the logarithm as the sum or difference of logarithms. In other words, we're going to expand this or expand these logarithmic expressions using those properties we had above. So we're going to be starting from this side and expanding to this side. So from here to here. Log base 4 of x plus 1 squared. That exponent can be brought down as a coefficient. So this is 2 log base 4 of x plus 1. And that argument of x plus 1, we can't split that up. So this is as simplified as it's going to get. Log base a of 4xy squared. So 4xy squared is that argument. All of those are being multiplied. So we're going to expand this using addition. Log base a of 4 plus log base a of x plus log base 4 of y squared. Make sure you are consistent with your base. And then that exponent on our y can be brought down as a coefficient. Log base a of 4 plus log base a of x plus 2 log base 4 of y. And in some situations, I've seen programs that want that log base 4 or log base a of 4 to be written as log base a of 2 squared or 2 log base a of 2. I don't necessarily find that to be any more simplified than log base a of 4. However, if you're getting stuck and not sure, maybe you look to see if you can simplify the argument by reducing it using that power rule. Log base 4 of xyz cubed divided by the square root of w. So we've got a very complicated argument here. We've got some multiplication, we've got some division. So we're going to apply both the product rule and the quotient rule. Log base 4 of x plus log base 4 of y plus log base 4 of z cubed minus log base 4 of the square root of w. Now, we do want to remember that the square root of w is the same as w to the power of 1/2. And then we can use the power rule to bring down our exponents. So we've got log base 4 of x plus log base 4 of y plus 3 log base 4 of z minus 1/2 log base 4 of w. log base b of 3x squared over w to the fifth y to the fourth power. Similarly, we're going to use both the product rule and the quotient rule to expand this. So we've got log base b of 3 plus log base b of x squared minus, and I'm going to use parentheses here because I actually have two things in the denominator that are being multiplied. So this is log base b of w to the fifth plus log base b of y to the fourth. So by adding those parentheses, it does make it so that both of those, if we were condensing, would end up in the denominator. And now we can start using the power rule to bring down those exponents. I'm also going to distribute at the same time. So we have log base b of 3 plus 2 log base b of x minus 5 log base b of w minus 4 log base b of y. Natural log of x plus 2 cubed times x minus 4 to the fifth over x squared times x minus 2. I'm going to illustrate slowing this down just a little bit in this one. This is set up very similarly to the last example. So I'm first just going to apply the quotient rule. So we've got the natural log of x plus 2 cubed times x minus 4 to the fifth minus natural log of x squared times x minus 2. So all I've done is applied the quotient rule where the we can expand using subtraction. From here, we're going to apply the product rule, and this is where the parentheses would really come into play. So we've got the natural log of x plus 2 cubed plus the natural log of x minus 4 to the fifth minus, when I expand the natural log of x squared times x minus 2, I need to subtract the entire expansion, which is why we have those parentheses. So this is the natural log of x squared plus the natural log of x minus 2. And now we'll use the power rule and distribute to finish this up. We've got 3 times the natural log of x plus 2 plus 5 times the natural log of x minus 4 minus 2 times the natural log of x minus the natural log of x minus 2. Working the other direction, now we're going to take the sum and difference of logarithms and we're going to express them as a single logarithm. So here we're trying to condense. Log of 3 minus log of 4 plus log of 5 minus log of 6. I'm going to start by rearranging these terms because I like those terms that are being subtracted to be together. So I've got log of 3 plus log of 5 minus log of 4 minus log of 6. Looking at those last two terms, because they both have a factor of -1, we're going to factor that out. So we're kind of going to undo that distribution that we were using in the previous examples. So log of 3 plus log of 5 minus log of 4 plus log of 6. Now we can condense using the product rule. This is going to be log of 3 times 5 or 15 minus log of 4 times 6 or 24. And now we can condense the subtraction to using the quotient rule. This is going to be log of 15 over 24, which simplifies to log of 5 over 8. So again, I like to make it so that the very last thing I'm condensing is two logarithmic expressions being subtracted. So I can set up my numerator and my denominator as a quotient. Log of 2x cubed plus log of 3x squared. We're going to condense the addition with multiplication. This is log of 2x cubed times 3x squared. We're just going to simplify that product. This is log of 6x to the 5th. Remember, when we are multiplying two terms that have the same base, we're going to add their exponents. Natural log of 3x minus 1 minus the natural log of 3x squared plus 5x minus 2. We're going to condense this using the quotient rule. This is the natural log of 3x minus 1 over 3x squared plus 5x minus 2. And we're going to see if we can simplify this quotient now. So if I think about factoring the denominator, I've got the natural log of 3x minus 1 is in the numerator, and then in the denominator, this is going to factor to 3x and x. Factors of 2 are 2 and 1. So we want this one to be a 2, this one to be a 1. Our denominator factors to 3x minus 1 times x plus 2. And here we can simplify out that factor of 3x minus 1. So this is the same as the natural log of 1 over x plus 2. And a quick review of negative exponents, because we've got that 1 over x plus 2, this is equivalent to the natural log of x plus 2 to the negative first power. And we can bring that negative 1 out front to write this as negative 1 times the natural log of x plus 2. These properties are really important because when you get into calculus, you're going to end up having to rewrite expressions to be able to apply other tools such as differentiation or integration. So being able to manipulate the way that something is presented allows us to do additional things with that particular expression. 2 log of x plus 3 log of x plus 1. We're first going to undo the power rule. So those coefficients out front are going to become exponents on our arguments. So log of x squared plus log of x plus 1 cubed. And now we'll condense using the product rule. Log of x squared times x plus 1 cubed. Practice using some of those other properties. Log base a of a to the 7th power. This is just 7. Because this exponential term a to the 7 and this log of base a, because those bases are the same, they are undoing one another. The natural log of e is 1 because the base of our natural log is e. So this is asking e to what power is e? E to the first power is e. And then 7 raised to the log base 7 of 4. Again, the base of the exponential matches the base of that logarithm. So those are going to undo one another. This is equal to 4. These are really great properties to be aware of. It does help us simplify expressions a lot. Given that log of 2 is 0.3010 and log of 3 is 0.4771, find each of the following. We want to evaluate log of 18. We're going to be using the given values. So what we need to do is rewrite this logarithm so that we're able to write this as log of 2 or log of 3. So we're going to rewrite 18 as 2 times 9. So this is log of 18 is the same as log of 2 times 9, which is equal to log of 2 plus log of 9. The log of 2 I have a substitution for, but log of 9 I don't. But 9 is 3 squared. And using the power rule, I can bring the 2 out front as a coefficient. So this is equal to log of 2 plus 2 log of 3. And now I can substitute in the given values for log of 2 and log of 3 to evaluate this. 0.3010 plus 2 times 0.4771. And this gives me 1.2552. Log of 9 squared. When I think about that 9, I'm going to think about it as 3 squared again. So this is log of 3 squared being squared. And power to a power, we multiply those exponents. So this is log of 3 to the 4th power, or 4 times log of 3 using that power rule. Substituting in for log of 3 is 0.4771. And multiplying that by 4, we get 1.9084. Now, there are certainly different ways. I'm illustrating just 2 ways of looking at these examples. There might be additional ways that you want to look at it, and that's okay. But ultimately, we're trying to get this down to some expression involving log of 2 and log of 3. So we're trying to rewrite that argument and rewrite the expression so that we're just using the logs that we're given. Log of 12. I immediately think of 12 as log of 3 times 4. So this is log of 3 plus log of 4. Again, I don't have log of 4, so I'm going to have to try to work with that one a little bit more. I know 4 is 2 squared. So log of 4 can be written as 2 times log of 2. And now we can substitute in the values for log 3 and log 2. 0.4771 plus 2 times 0.3010 gives me 1.0791.